We all know neural networks. These belong to the connectionist approaches to artificial intelligence. On the other hand, we have symbolic AI, such as decision trees. But do you know hyperdimensional computing, or in short, HDC? This is a promising framework for machine learning applications, and especially for embedded devices. It tries to combine the advantages of the symbolic structured data representations and the connectionist distributed vector representations by representing data in a hyperdimensional space. Encoding the data to this hyperdimensional space is a crucial aspect for the performance of HDC. And it is already well known how to encode text data, numeric data, and time series data, but how to best encode images remains to be explored. During my PhD, I have developed a novel framework that uses a mapping technique for numeric data and a local feature extraction method. This proposed framework shows to preserve similarity of patterns at nearby locations. It outperforms other studies using native HDC, and it is more robust to noise and blur compared to the baseline. But before diving into how HDC works, but before explaining how do we encode the images, let's first introduce HDC. Then we can take a look how binarized images can be encoded in the hyperdimensional space, and then we can test and compare it to the baseline encoding. So what is HDC? For classification, it has two main building blocks. First of all, we have the encoder. This maps input data to hypervectors. These are vectors of typically 10,000 elements, and in my case, I focus on binary dense vectors, meaning that they have values of 0 and 1 with an equal probability of both. The classifier is responsible to create class prototypes during training and will compare all the vectors to all the stored class prototypes during the inference. And as I said, the encoder is a very crucial aspect for the performance. So how should we encode binarized images? First of all, we need to encode the pixel values, which are in a binary image, of course, only 0 and 1, and they do not have any numeric relationship, so we can just assign two random vectors for both values. However, when we would like to encode the position of the pixel, we of course want to make sure that we encode it as such that two pixels close to each other are more similar than two pixels far away from each other. This is typically done with linear mapping, shown here on the left, where you see that the similarity to the pixel at position 2111 linearly decreases the further away you go from that pixel. This is, however, not ideal when we work with large images, because then two adjacent pixels are just very small in difference of similarity. For that, we introduce local linear mapping, for which we split the x and y axis in a certain number of splits. And this number will then determine the radius in which the similarity is able to decrease the further away you go from that pixel. Binarized images are then encoded by a point of interest selection. Namely, we will create a patch of a certain size around all the pixels with a value of 1. We will encode this patch into a patch vector and use this to encode the binarized image, by still taking into account also the global position of the patch. And for that, we use the local linear mapping that I just explained. Is this an improvement compared to the baseline? Well, if we look at the baseline pixel-wise encoding, we see that the accuracy of 60% with the splits equal to 1, so linear mapping, is increased to 97.5% on the MNIST dataset with our proposed framework with a patch size of 7 and 4 splits in the local linear mapping. When comparing this to the literature, we see that this outperforms other studies using native HDC, and it is on par with methods that use more complex or hybrid HDC methods and other lightweight machine learning methods. We also tested the robustness of this method for 5 different types of noise and blur, where we see that our proposed method is able to perform better than the baseline, and the difference compared to the identity, so no noise, is smaller than with the baseline encoding. So now that we have seen how HDC works, how binarized images are encoded into the hyperdimensional space, and how it performs compared to the baseline encoding, we can conclude that the proposed encoding framework preserves similarity of patterns at nearby locations, it outperforms other studies using native HDC, and it is more robust to noise and blur compared to the baseline encoding. So now not only text data, numeric data, and time series data, but also binarized images can be encoded into the hyperdimensional space.